Okay, let's get started. Can anybody tell me what we're up to? What are we doing? What are we talking about? Anybody remember where we are? Rishi, go ahead.
We were working our way up to the Heine-Borel theorem.
Yes.
So that
Going up to
the
Heine-Borel.
compact subsets of Euclidean space are those that are closed and bounded.
Okay, yeah, we're heading towards Heine-Borel, which is sort of like a characterization of compactness. Right. And what's the last thing we did? Somebody other than Rishi? Is he?
We just proved all K cells are compact.
All K cells are compact. All K cells are compact, and yeah, okay, yeah, all K cells are compact. And along the way, we proved this thing that if you have compact sets, so recall we had this thing that if you have a bunch of compact sets and they have a finite intersection property, then in fact their intersection is going to be non-empty. Right. That's something that we showed along the way. Yeah. Okay. So yeah, it's in fact true that so we could sort of make a little corollary to this, that if K is compact, then every collection of subsets, every collection of closed subsets with the finite intersection property has a non-empty intersection. Right, so that's a corollary, right? Like, you know, if your set is compact and you're looking at, hold on, people are copying. If your set is compact, right, then you know that any closed subsets in there are going to be compact themselves, right? And so we can just apply the previous result. You know, if you've got compact sets with a finite intersection property, then the infinite intersection will be non-empty. So right, so if your set is compact, every collection of closed subsets with the finite intersection property has a non-empty intersection. Is that clear? That follows immediately from this, plus the fact that closed subsets of compact sets are compact. Right. In fact, there's a converse to that. So if your set has the property that every collection of closed subsets with the finite intersection property has a non-empty intersection, then that actually ensures compactness. Okay, I'm not going to prove that, but that's another way of thinking about compactness. Okay, so there's a converse to that. Compactness is the same thing as this property about closed subsets. Okay, let's get to the Heine-Borel theorem. So we'll say it like this. In Rn, the following are equivalent. Okay. The following statements are all logically equivalent to each other. Okay. So first, E, a subset of Rn, is closed and bounded. 2, E is compact. And 3, E is limit point compact. In other words, every infinite subset of E must have a limit point. Every infinite subset of E has a limit point at E. Okay. And which parts of this do we know already? Which parts of this do we know already? Some of these things, these implications, we already have. Yeah, Mike.
Don't already know 1 implies 2.
1 implies 2. I don't know if we actually have got it completely. We're not far. We're within spitting distance of it, for sure. But I don't think we've stated it explicitly. Harrison.
2 and 3 imply each other.
2 and 3 imply each other. We've definitely shown 2 implies 3, right? We showed that if you're compact and you have an infinite subset, then there's got to be a limit point, right? We had that argument like if there's no limit point, then you cover each point with a set that contains at most 1 point of E, and then E would have to be finite, right? E would have to be some finite set. So we've done that. Do we show that limit point compactness implies compactness? I don't think we actually did that. Yeah, we've gone 2 implies 3, but not maybe 3 implies 2. Anything else? Anything else we've gotten? We've shown that compactness implies closed. That's definitely true, right? What about compactness implies bounded? Can anyone give me an argument that shows compactness implies bounded? Maybe see if you can come up with one. Compactness implies bounded. Just as an exercise about compactness. Let's see how well you guys are getting the idea of compactness. Yeah, or just talk with somebody for a minute about how you might do that.
Or foundations that have used in the
I was thinking like if you had like a finite set.
if given any cover, finite subcover.
I don't find that you can't cover it. Doesn't that mean that it's bounded? Like finite, you
Just pick the subcover.
I don't know. I am wearing
Yeah, anybody come up with something? Anybody have an idea? Compactness implies bounded. You're in Rn, right? You have some compact set. You want to show that it must be bounded. Somebody other than Rishi? No? Anybody want to make a guess? Like, yeah, go ahead. Yeah, Izzy, go for it.
Well, bounded is that E is in some neighborhood of
Yeah.
an X. So
Yeah.
if you just pick that neighborhood big enough to cover it, then it's compact.
Well, you gotta use the compactness. So
Well,
remember,
it's compact, which there's an open cover, then there's some finite cover. If you pick that cover to be the really big neighborhood, then it's bounded.
so yeah, so let's make this proper, right? So like you say, well, you want to show it's bounded, right? And so you know it's compact. It has this weird property that no matter what open cover is chosen, there is a finite subcollection that still covers, right? No matter what open cover is chosen, there's a finite subcollection that covers. So what's your open cover going to be? You want to choose an open cover that covers this thing. Let's make it like,
Just like,
what is it? Let's pick some x. We're going to make some sort of cover, and it's gonna cover this guy. How are we going to cover this guy? We need to make the cover, right? If we're doing compactness, we got to make an open cover. What's our cover? How are we going to cover it? Let's just cover the whole space. Okay, we're going to cover the whole space. How are we going to cover the whole space?
Ryan.
Yeah, but you want to make an open cover. Are you just gonna throw in all of Rn? That's the cover. The one set. Harrison?
Neighborhoods of X.
Neighborhoods of X? All neighborhoods of X. Okay, so let's like take all neighborhoods, let's say like all neighborhoods of X like with radius 1, 2, 3, 4, 5, etc., right? Let's take that as a neighborhood. So radius 1, radius 2, radius 3. We know that this is going to cover the whole space, right? Right. This covers all of Rn, so certainly covers K, right? Covers K, and so you know that there's some finite subcover, right? So K is compact, so you know that there's some n1 x, n2 x, r x covering K, right? So there's some radii that cover K, right? Like maybe this radius and this radius. That's enough maybe. So take the largest one, right? Take the largest one. That one contains everybody else, right? And so that one contains everybody else, and so whatever that one is, let's call it n sub max r and I. This thing, this neighborhood covers K, right? And so we found that K sits inside of a ball, i.e. K is bounded. Okay. Okay, so I hope you guys are kind of getting a sense of how to use compactness, right? Compactness is, it's this nice property that whatever open sets cover your set must have a finite subcollection that still covers your set. Okay. Yeah, it takes some time to get used to. Yeah. Okay. So so compactness implies closed and bounded. What about closed and bounded implies compact? That's the one that we said we're kind of pretty close to. So the hint is we can use this property. We just showed that all K cells are compact. Okay. Suppose you know that your set is closed and bounded. And you know that all K cells are compact. You already know all K cells are compact. So let's prove 1 implies 2. So assume E is closed and bounded. Thus E is compact. Using that K cells are compact. Okay, talk for a minute with a neighbor about how you might get from here to here via this.
How can we relate?
This one's bounded. Yeah.
Oh, yeah. Oh, is that what that is?
So in this case.
Yeah, okay, so it's inside of a ball.
Yeah.
That makes so much more
So-
sense. I've just been like, I don't know, maybe it's like, if it's 6, it's a hexagonal. Nine, it's a non-real. I was just coming up with
So,
something.
yeah, K cell, it's called.
That makes more sense.
Anyhow.
You know, E is inside of it, it's closed and
So we're using
bounded.
the K cell as boundary.
Yes.
The K cell is
And
boundary.
it's, oh, a closed subset of the compact. Uses compound and
So if you close the back,
inside
it's
of
that.
it.
It has to do with it. That's a case.
Okay, anybody figure it out? Other than Rishi? Rishi, you're banned from speaking. No, you should be. No, I'm kidding. But even if I were not kidding, you should just be like, yes, I have been banned. Right? Like that's a mark of honor. Yes, Mike.
I guess we would like try and find some K cell that where E is a subset of that K cell,
Exactly.
and then since it's a closed subset of a compact set.
Done.
Yeah.
That's it. That's it. Right? Right? How do you know that there's a K cell that contains it? Because E is bounded, right? E is bounded, so it's contained in some K cell, right? Just you know it's contained in a ball. Just take a K cell that contains the ball, right? Right. So it's a closed subset of a compact set, and thus is compact. That's it. Okay, so that's why I was saying to Mike earlier, we're basically there already. Right, so to write this down properly, E bounded will imply that E is contained in some K cell. K cells are compact, and E is closed. And we already saw that closed subsets of compact sets are compact. Okay, yeah, Rishi.
So I know we were showing this for Rn,
Yeah.
but it looks like the primary fact we're employing here is that balls are subsets that balls are subsets of some things we already know to be compact. Are there other spaces or other metrics or something in which we might not necessarily have K cells, but we can still have this?
Yeah. I mean, as you see, we really needed to be able to prove that K cells were compact first. So nothing in general, I'd say. I can't think of anything in general. Yeah. That's a good question. Yeah. Just to make sure that you guys are getting the notion of compactness, while I was outside, I thought maybe I'll give you this question. So suppose you have, so we'll finish this up in a second, but just to make sure you guys are getting compactness. So suppose you have f, a function on a compact set. Okay, so k is compact, and you know that f is bounded. You know that for every x and k, there exists some neighborhood, n Rx, x, on which f is bounded. Okay, so f is a bounded function, right? It doesn't, that is for every x, right? For every x, you know that there's some neighborhood, and in that neighborhood, there's a max and then there's a min for your function. Right? Your function doesn't go off towards infinity. Okay, your function is finite on. There's a neighborhood on which your function is bounded. Okay. Okay, so show that f is bounded on all of k. There's a bound that works for all of for the whole set k, right? You know that the function's bounded on for every point. You know the function's bounded locally, right? For every point, there's a little neighborhood around you where it's bounded, right? You also know that the set is compact. Show that it's actually bounded globally. Okay, and this is really the point of compactness. It allows you to pass from local to global. Okay, you've got some sort of local property, you patch it together, and you get a global property. Okay, if you can do this, then you understand compactness. I'll go outside again.
I have two things, I don't know which of the two it is. What's some neighborhood at x, or do you take every neighborhood for the 1 point x?
What's so X?
You know what I mean?
X is point in all.
Between those two though, and then you just use that your open cover.
Oh, yeah,
And
yeah,
then
so X
there's,
and K.
you just take the, it would have to be you take one x, and you take a bunch of really, like,
A
a
neighborhood
bunch of
in
neighborhoods
all.
for the 1x.
Yeah.
You take the max one, it's gonna cover the whole thing, and it's finite.
Yeah.
So I feel that sounds right.
Yeah. Logically, that makes sense. This process always works in all.
That is good. I was saying, I feel like,
So
my only question is,
F is
you take the union of every, of like one thing at every point, one
So
neighborhood?
for every
Wait.
point, if there's a
Every
neighborhood where
neighborhood
it's bounded, and the k is compact, then can we take all those neighborhoods? Like, f is bounded in all those neighborhoods, so we just add all
So
the
my
neighborhoods
question is, are you taking like one neighborhood for every x, or are you taking
So then f is
like just a bunch of neighborhoods for the one x, and the neighborhoods for each of that?
Does that even make sense? Like, I don't know. Do you see what I'm saying? Like, for every point, there's an actually where f is bounded, and if you
Take whatever,
those neighborhoods
oh,
together,
oh,
we'll get like a big.
I think yeah. Like, so you take the like r x, and then point y, take the r, the radius y, and then you put them all together.
Okay.
And then you union them, and then you got.
I really don't give a yes.
Compete.
I don't know why. So F is bounded. I thought F would be bounded. Oh, to take back.
I have them.
Okay, anybody have an idea? Yes?
No, we're good.
Should I?
Yes.
All right, so I don't know if I can explain this clearly, but
That's okay.
for every x in this compact set K, right, we have a neighborhood. We also know that since K is compact, right, then for any infinite, open cover, there's a finite sub collection, and we can take the union. Or if we take the union of all those, we can like take the union of all these neighborhoods. Yeah. Is that?
It covers K, so, right, you've covered K, right? You have your set K, you've covered it with all these intervals. There's infinitely, at this point there are infinitely many of them, and on each one of them, the function is bounded, right? There's a little bound for every.
We know that K is compact, so that means we can choose a finite one, and then thus the whole thing Thus, since each one of these is bound, the whole thing is bounded.
Exactly.
Okay.
Dun, dun, dun. Very good. Good. Right? So there exists, because by compactness, you know that we can just limit ourselves to there's a finite number of guys that still cover the set. Right? There's finitely many of them that cover the set. So let M be the max of the various maxes, right, of M1 through Mn. Yeah.
So is it like you're like going through all, like you have all these intervals and you're just kind of getting rid of the ones that like already counted before? You're just
That's the
crossing
thing,
out?
because it's compact, there's only finitely, you can throw out
Okay.
all but finitely many. That's the
Gotcha.
point. Okay? If it were not compact, you wouldn't be able to do that, because you might have something like this,
Yeah.
right? And then you have to include all of them. You'd have to include the infinitude of them. Okay? Yes.
Why can't you just pick the one big one?
What one big one? There is no one big one. So here's your set.
Okay.
Here's your non-compact set E.
Great.
Okay. Here are your
Oh, okay.
right.
Makes more sense.
In the union, they cover the set,
Gotcha.
but
I
you
thought
cannot
they were
take
going that way.
you cannot take
That
any
makes
finite you cannot take any finite subcollection of them and still cover it.
Yeah, it makes sense.
Yeah.
Can you explain f being bounded, like a function being bounded? Does it mean like the image or the?
Yeah. It just means that the output is trapped between two values.
Okay.
Right, so like you have some function, right? It's trapped between two values, right? It doesn't go off to infinity, say. Okay, great. Okay, I think you guys are starting to get it. Okay, so now let's do the last part of this proof. So we actually didn't even need to prove this backwards direction here, because what we're going to prove next is that 3 implies 1. Okay, so we have that one we just did just now, well, a few minutes ago we did 1 implies 2. We already had 2 implies 3. We'll show that 3 implies 1, and that will complete the logical circuit. Okay, so so we want to show that 3 implies 1. In other words, that if E is limit point compact, then E is closed and bounded. Okay, so we're going to do this in pieces, and we'll say, well, let me call it A. Suppose E is not bounded. Okay, suppose E is not bounded, and we'll show that E is not limit point compact. Okay, so suppose E is not bounded. Okay, suppose E is not bounded, then how can we, right, what does that mean? That means that, that we could take a sequence of balls expanding outwards, right? And no matter what ball you take, there's going to be some point of E that's not contained in there, right? So one can create a sequence of points, piece of n, that in E that head off towards infinity. Right, in the sense that we can arrange it so that, say, piece of n is always bigger than n. Right, because it's unbounded, right? So it's not trapped no matter what ball B sub n 0 we take, we know that there's some P sub n sitting outside that ball, right? I mean, we should call it E sub n because they're points of E. Okay, we know that there's some point E sub n sitting outside that ball. Okay, right? Those guys go off to infinity. There's no limit point, right? There's no limit point. So these guys, so we have no limit point. So we violate limit point compactness. Right? Limit point compactness means that whenever you have an infinite subset, that infinite subset has a limit point. Well, we've just created an infinite subset of E that has no limit point failure. Okay, so now so we know that E has to be bounded. But let's now suppose that E is not closed. Suppose E is not closed. Okay. Then we know that then there exists some point. Yeah, there exists some point x naught that is in E prime, so it's a limit point of E, but it's in E complement. Okay, so a limit point of E, but in E complement. Right? Right. Closed means you contain all your limit points. So suppose there's some limit point that you don't contain. Okay. So we have this point x naught, right? And it's a limit point of E, right? Okay. So anybody think of what we can do with that limit point? What can we do with this limit point? We should go ahead.
I'm not sure if this will work, but
That's
maybe since x naught is a limit point, we know that for any radius, the punctured neighborhood will intersect E at some point other than x naught, which we already know because x naught is not in E. So we could perhaps take the point guaranteed by that for every, say, natural number radius, and then that might give us
some sort of problem.
Yeah.
It will. Okay, so yeah, you say, well, look, we know that every punctured neighborhood contains a point of E, right? That's what it means to be approximable by E, right? To be a limit point of E, you're well approximated by E. So we create a sequence of points E sub n again in E, such that the E sub n, the distance of E sub n to x naught is smaller than 1 over n. Okay, so these guys are heading off towards x naught, right? And okay, so we have this infinite sequence, right? We have this infinite sequence of points inside of E. We also know that E is, right, so E was supposedly, E is limit point compact. Right? Right, we're assuming E is limit point compact, we're trying to show that it's closed. Right, so the limit point compactness, we've got our infinite subset, so we know that there's got to be some limit point here. Right? So, E is limit point compact. E is limit point compact, so we know that there exists some point y in E that is a limit point of those points E sub n. Okay, so okay, so there's some point y. There's some point y that's a limit point of the e's. Okay. Give me a second. Okay, so we want to show that that has to be the we want to show that x naught must be y. Right? Yeah, I had proven this one way, and then I realized actually we cannot prove it that way. Sorry. So let me go back to my notes here. Okay. So let's see. So consider the distance between E sub n and y. Okay. That is greater than or equal to the distance from x naught to y minus the distance from x naught to en. Right, wait, hold on. So give me 1 minute, and let me make sure that I know what I'm talking about. And then I'll see. Right. Okay. So what's going on here is that we've got the E sub n, we've got x naught, we've got y, right? And the length from E sub n to y is bigger than the difference between x naught to y and x naught to E sub n. So this is part of the triangle inequality. So the length of one side is greater than to the difference of the other two sides. Other two lengths. Okay. So this thing here is, now this thing here, we know that this distance is smaller than 1 over n, right? This distance here is distance here is smaller than 1 over n, right? So if we subtract off 1 over n, it gets even smaller. Okay, gets even smaller, and then choose n large enough. Choose n large enough that that this is going to be bigger than 1/2 of this. Okay, so what does that give us? That gives us that, right, so that gives us that, that the E sub n, correct. The point is that if this is non-zero, so if this is non-zero, right, if this is non-zero, then the E sub n can't get close to y. Right. Then, right, this is some constant, delta. Right. This is some constant, and so the E sub n can't get close to y. Okay, does that make sense? The way I was thinking to do it, and actually I realized this is not going to work, was to say, well, look, right, the E sub n are approaching x naught, right? The E sub n are approaching x naught, and then the y is the limit point of the E sub n, so the E sub n are approaching y. And so you can say, well, look, the distance between them is becoming arbitrarily small. The distance between these guys is also becoming arbitrarily small, right? And so you know that the distance between these guys by the triangle inequality would be arbitrarily small also. Okay. But I think you have to be a little bit careful. I was being a little bit reckless because you have to you have to create a sequence. You have to be a little bit careful about creating the sequence. So anyway, okay. Anyway, so this is okay. Okay, it's okay. Yeah, that is it. Sorry.
Go from, can you just repeat the last part after you choose the n large enough? I just don't understand how that shows that they're going to be the same.
Yeah. So the thing is that this thing is a constant, right?
Yep.
This thing is a constant. So choose n large enough that 1/n is smaller than half of this.
Mm-hmm.
Then you're going to have this minus something smaller than half of this. So the difference will be greater than half.
Mm-hmm.
Right? So, right, you have some number, x naught minus y, right? And you have this 1/n, right? So choose your 1/n so that it's basically, choose your n large enough that 1/n is basically nothing. Okay. Well, then you subtract off that nothing, you know that it's going to be bigger than 1/2 of that. Right? So just choose 1/n so that it's smaller than half.
Okay.
Yeah. Okay. Sorry. Okay. So that's the end of the Heine-Borel theorem. Okay. Any questions? That was kind of the main point. Yeah. So we introduced all these topological definitions, and then main thing was to get the idea of compactness, right? So make sure that you understand what compactness is, and then the other thing that we're getting is sort of different characterizations of compactness, right? So we have limit point compactness, right? We've got this closed boundedness, right? And we've got also, although I didn't prove it, the finite intersection property for closed sets. Yes. Yeah. For collections of closed subsets. Okay. So that's those are the big ideas. There's one more thing in this chapter that doesn't play that big a role. But it's still a concept that you're going to encounter if you do say like complex analysis or if you do some topology. Yeah. So let's do it. It's the idea of a connected set. So what does it mean for a set to be connected. Okay, so okay, so the definition is a little bit peculiar, but you say, suppose you have a metric space and you have two subsets. Okay, you have two subsets. Okay, here's definition one. If the closure of the first guy intersect the second guy is empty, and the closure of the second guy intersect the first guy is also empty, then we say A and B are separated. Okay, so for example, suppose you're in R1 and you have these two open sets here, A and B. Okay, are they separated? So that these are like they've got the same endpoint here, right? Like AB, and BC. Are they separated? Yes, they are. Yes, they are. People are shaking their heads, but right, the closure of this guy is just that, but it doesn't intersect this open set, right? Right. The closure of this guy is that it doesn't intersect this open set. It's true that if I took the closure of both of them, that would intersect, right? But that's not what we're saying here. Closure of one intersect the other guy, closure of the other guy intersect this guy, then they're separated. Okay. So example A, B, and BC are separated. Right. But if I have something like AB closed and BC open are not. Right? Because the closure of this guy would intersect this guy, even though the closure of this guy doesn't intersect that guy. So, okay, so now we can define what connected means. If a set can be expressed as a union, so notice that remark separated definitely implies disjoint, right? Because it means the closure of one does not intersect the other guy, right? So certainly the original sets don't intersect each other either, right? So separated definitely implies disjoint, but disjoint does not imply separated, as we saw in the second example. Okay. So coming back to the definition of connectedness, if E can be expressed as a union where A and B are separated, I think this is usually called E has a separation. Then E is called disconnected. Okay, E is disconnected. So, for example, right, this set we have over here, AB union BC is clearly disconnected. because we saw that these guys were a separation just now. Okay. And if E has no separation, then it's called connected. Okay. So there's no way to express it as separated sets, right? So no way to express as separated sets. Okay, for us, the main application of this concept will be when we talk about the intermediate value theorem later on. Okay, right? Do you remember intermediate value theorem? You have some continuous function. You have some continuous function, and it takes on two values at two different points. Then it must take on every value between the output values. Right? Like if this is f of a and this is f of b, and I choose any intermediate value, gamma, there must be some point where you attain that gamma, right? Intermediate value then. So that will follow from showing that continuity and connectedness work together nicely, in the sense that the continuous image of a connected set is still going to be a connected set. Okay, so like this connected set here is going to get mapped to a connected set up here. Yes?
Is there a particular reason that we use this definition with separated sets instead of just talking about like disjoint open sets?
Disjoint open sets, I mean, that's not going to capture the idea, right? Maybe I'm not understanding. Like, if you're just talking about, so let's think. Right? Do you mean to say like, let's call it separated if they're disjoint open sets?
Yeah. Because I don't think the criteria is precisely equivalent, but I think we get the same spaces are connected.
I don't think so. Yeah, I don't think so.
Okay.
Yeah, I can't think of an example off the top of my head, but I don't think so.
Okay.
Yeah, sorry, I wish I could come up with an example.
That's fine.
Okay. Okay. So the theorem that's going to be relevant for us is the following: that that in R1, a set is connected if and only if for all pairs of points x, y, and e, the whole interval x, y is contained in E. Okay, so whenever you have 2 points, right? Whenever you have 2 points in the set, then everything between them is contained in the set. Okay. This is basically saying that connected is equivalent to something called path connected. Right, that the whole path between those 2 points is still in the set. Okay. 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 The proof of this is not too exciting. You say, so in the forward direction, suppose that the path connectedness fails. Suppose that there exists some point z that's between x and y, and z is not in E. Okay, then you can create a separation, right? Then E is disconnected. Just take 0, I'm sorry, negative infinity z intersect E, and z comma infinity intersect E. These guys, these guys form a separation, right? So it's just, if there's some point, if you've got these 2 points x and y, right, and then there's some point in the middle that's not contained in it, well, just you can split your set. You can split your set into two parts that are separated. So that's nothing fancy. Everybody all right? This is not the most exciting part. So if you're starting to lose it, it's okay. Okay. Backwards direction, right? So suppose that E is disconnected. So again, we're going to do contraposition. Right. Suppose E is disconnected. Right? And we'll show that there's some point that fails. Okay. We'll show that there's some point that fails this thing here. Okay. So we want to show that there exists x and y in E with some bad point, bad z, right? That's not in E, and z is between x and y. Okay. So what we do is we right. So what we do is we say, okay, we've got some set A, we've got some set B. Okay, pick 2 points, x and y, where x is in A and y is in B. So pick x and A. Right, so we know that E is equal to A union B, and that these guys satisfy the disconnection. Right. So pick some x in A, pick some y in B, and without loss of generality, we can assume x is smaller than y. Right? One of them has to be smaller than the other. So, okay. So now we want to create the z, right? We want to create the z. So what we're going to do is we let z be the supremum of A intersect the interval xy. Okay, so we take this interval xy, right? We look at everything that's in A in here, right? All the points of A that are in here, we take the supremum of those points. Okay. Okay. So, okay, the supremum of A intersect xy is contained in the closure is contained in the closure. We saw this earlier, right? The supremum of a set is going to be in R1 is going to be contained in the closure of that set. Okay. That in turn is contained in the intersection of the closures. I think we might not have proved this, but just leave it as an exercise, that the closure of an intersection is contained in the intersection of the closures. It's easy to see. Okay. So what does that tell you? That this point Z is contained in A bar, right? Z is contained in A bar. And in that case, Z is not contained in B, right? Because A bar and B don't intersect, right? So we have this point that's not in B. Okay. So we get this point here, Z. We know it's not in B. Okay. Now there's two possibilities. If Z is not in A, then we're done. Right? Because right? Because E is A union B, right? Remember what we're trying to do, okay? I should remind myself what we're trying to do. We're trying to show that, you know, if E is disconnected, I'm sorry, we're trying to show, yeah, that if, we're trying to show that if E is disconnected, then there's some point that's not in E where there's some point between X and Y that's not in E, right? Right. That's the goal. We want to show that there's some point that's between X and Y that's not in E, right? So we've got the X and Y. We found this point. It's not in B. If it's not in A, then it's not in E, and then we're done. Okay. Okay. So now, if Z is not in A prime, right? If Z is not in A prime, then we know it's not a limit point. It's not a limit point of A. Right? It's not a limit point of A, and so we know that we can find a neighborhood around it that doesn't intersect A. Oh, wait, sorry. Sorry, I'm sorry. Let me take that back. So sorry. If Z is in A, then we're done, right? I'm sorry. If Z is not in A, then we're done. If Z is in A, right? If Z is in A, here's the point. Then Z is not in B bar, right? Because this was a separation, right? Okay, so then Z is not a limit point of B. Okay, so what does that tell you? That tells you that that there's some neighborhood around it, right? So there's some neighborhood around it that doesn't intersect B, right? So then there exists a point Z prime that's bigger than Z, such that Z prime is not in B bar. Okay. So what do we get? We get a point. We get that x is less than z is less than z prime is less than y, and this z prime is not it. It's not in A, and it's not in B either. Sorry, we should just be.
How did we get that Z prime is not in A?
Z prime's not in A because remember what Z was, right? Z was the supremum,
Oh.
right? Z was the supremum of the points in A in there, right? And Z bar is bigger than that.
Okay.
Yeah. Okay. Should I say it again? Should I say it again, or yeah? Let me say it again. Okay. So we're trying to show that if E is disconnected, then we can find 2 points in E where there's some point in between them that's not in E. Okay, that's what we're trying to show. And so we say, okay, being disconnected means that there's a separation, right? It can be expressed like this. So choose some guy X in here, choose some guy Y in here. And without loss of generality, X is less than 1. Okay. Now play this game of taking the supremum. Okay. Take the supremum of all the points of A that are contained in this interval xy. Okay, that's our Z. That's our candidate, and it may or may not work. Okay. So thinking about the closure tells us that that Z must be in A bar. That Z must be in A bar, right? Okay. Being in A bar means that it's not in B. So we know that this guy is not in B already. If it's not in A, we're done, right? So like if it's not in A, then we're done because we're trying to show that this point is not in E. Okay. So if it's not in A, we're done already. If it is in A, again we use the separation, and we say, well, being in A means that you're not in B bar, right? In other words, you're not a limit point of B, and so there's some little neighborhood around you. There's some little neighborhood around you that that doesn't intersect B, right? So you can choose somebody to the right of you, right? You can choose somebody to the right of you that is not in B. That guy is not going to be in A because Z was the biggest guy inside here. And I guess you choose your neighborhood small enough, then you don't go past Y. Okay, so there's a little, so choose a small neighborhood. Choose a small neighborhood, right? Small enough that you're still sitting inside of this interval, right? Then you know that there's going to be some guy Z prime there. It's not in A, and it's also not in B. So you found the point. You found the point that lies between these two guys and is yet not in E. Okay. Okay. Sorry, sometimes I get panicked myself and then I don't explain that well. Yeah. Yes?
Could there be like more than one point in this like
Sure.
middle space?
Yeah, in fact, like loads of points.
Okay.
Yeah, but we just need one.
Yeah.
Yeah. Yeah, but good, you're seeing it. Okay. Okay. So we have 5 minutes. Okay, so I'm just gonna start. So I always, when I teach this material, I always jump from chapter 2 to chapter 4. So we're going to jump from chapter 2 to chapter 4 into continuity. So chapter 4, continuity. So the way the book is structured, we go next into sequences and series. Okay, so chapter 3 is sequences and series. But the kind of negative about that is that really you use this stuff about compactness and everything in chapter 4. And by the time you get to chapter 4, you have forgotten, I think, everything that you know about compactness. So what I usually do is chapters 4, 5, and then I compact it chapter 3, which is sequences and series. Sequences and series. And then I go to chapter 7, which is sequences and series of functions. So just to keep the ideas together, right? Go right from sequence and series to sequence and series of functions, right? Go right from topology into continuity where it's really used. Okay, so that's how I defend my choice. Yeah, I think it makes sense. Although, I mean, there are books where they just go to sequences in series first, like instead of topology, go to sequences in series first, and then to topology. But anyway, so should I even talk about it? No, I'm not going to talk about it. We'll see you guys. So anyway, next time, chapter 4, continuity.
As somebody with the memory of a goldfish, I thank you.
What?
Somebody
Oh,
with
the memory of a goldfish. I
goldfish.
see.
And forget everything.
Sorry, I thought you said memory of the goldfish. And I was like, is this something that...
So you don't know the goldfish?
Right.
Obviously, everybody knows the goldfish.
Yeah.
I guess I don't have the memory of the goldfish.
Harrison, are you doing anything for Chinese New Year?
I'm making food.
My parents gave me $100 DoorDash gift card, and that's maybe the best.
Bye-bye.
I should do good at my dear bro. I don't like this stuff. It doesn't taste good.
Okay, well, unfortunately, some of our mothers think some of us can't cook, not naming food, not naming names, but and that might